Hello and welcome to Comprehensive Rocket Science. My name is Rob Roundtree. So today I wanted to go over some news topics. This channel is generally dedicated to more educational content, but really equations and really getting into the nitty-gritty of rocket science. But there's just been so much happening in November that I wanted to cover stuff. So yeah, a lot of awesome things happened, and I'm excited to talk about some of them. Alright, so the first thing to talk about is the James Webb Space Telescope. So just give everyone a quick rundown on what it is. It's a space telescope being jointly developed by NASA, ESA, and Canadian Space Agency. I'm sure there's different levels of funding involved and corresponding different timeshares on the satellite, because that's how this typically works. Like with Hubble, certain scientific agencies will get time slots allotted. Those are very precious time slots, as you can imagine, to those people doing that research. But I imagine, NASA will direct a certain amount of time on the telescope, as will ESA and Canadian Space Agency. So it's often referred to as the replacement for Hubble. That is kind of true, because Hubble obviously is nearing the end of its useful existence, and James Webb Space Telescope is coming on at about the same time. Interestingly, because it was supposed to be out a lot earlier. A lot earlier. I think the initial launch was 2007, so 14 years ago. Almost 15. Anyway, the original cost was $500 million, and it's been about $10 billion now is the estimate. So small problem in acquisitions. It's not major though. It's fine. Anyway, sorry for my little rant there. It is arrived in French Guiana to be launched on an Ariane 5 launch vehicle on December 22nd. So the launch date originally was like December 17th, but they moved it back several days because there was an incident, and we'll talk about the incident in a minute. Just a quick rundown on the James Webb Space Telescope in general. So it consists of 18 hexagonal mirror segments, and that it basically has to unfold these in flight, which will be interesting, and hopefully it all goes well. But that these different mirror segments allows the mirror to be much larger than that of the Hubble Space Telescope. So the Hubble Space Telescope had a 2.4 diameter meter, whereas the James Webb Space Telescope has a I believe 6.5 meter diameter mirror. And then, if you know anything about optics, the resolution that you get is basically directly proportional to the diameter of your mirror. So that's a huge difference, on more than almost a factor of 3. All right. So while we're talking about it, I just want to anchor down on resolution a little bit. So your optical resolution, your angular resolution is directly proportional to your diameter of your primary optic. So as you increase the aperture size, as you increase your exposure time, eventually your resolution will become limited by diffraction. And for diffraction, you can use the Rayleigh criteria, and which is the Airy disk is the basically the case of Rayleigh criteria as opposed to applied to a circular aperture. So this ends up being that your angular resolution, so the angle that two objects have to be apart in order for you to see them, is equal to 1.22 times the wavelength over the diameter of your optic, where wavelength and diameter are obviously in the same units. So what you see there is diameters on the bottom of that equation. So as you increase your diameter, you are getting a linear decrease in the angle that two objects need to be apart in order for you to be able to make them out as separate objects. So that's part of the reason why James Webb Space Telescope, being a much larger object, makes such a big difference. Is you'll be able to break things out that are almost 3 or 1/3 of the distance from each other as viewed from Earth. So Hubble was designed for sort of the ultraviolet to infrared to near infrared spectrum. It would be in the 0.1 micrometer to 1 micrometer which is roughly it's near ultraviolet and near infrared, and then a lot of visible. So that's why a lot of the things you'd see from Hubble Space Telescope were actually visible light images. So the way that like spectral imaging works is you have sensors that are sensitive to one particular wavelength, and that wavelength is given a color. So say you have your 400 nanometer, or sorry, 400 nanometer sensor, right? So this particular sensor is the wrong word here. It'd be like a you can think of it almost as like a material, basically something inside the actual inside the optic. Basically the sensitive small sensitive piece that's taking in the light. So you'd have something that's sensitive to 400 nanometers, maybe something sensitive to 550, and something sensitive to 700, as well as several others, because like I said, it's 0.1 micrometer, which is 100 nanometers to 1 micrometer. Anyway, as you know, the visible light spectrum is 400 to 700 nanometers, so that's why I use that example. But say if you had a 400, a 550, and a 700, your 400 would be color-coded violet, your 550 would be color-coded green, and your 700 would be color-coded red. And then using the different amount of those three colors, you could create a true color image, basically a representation of how something, the way it actually looks, the way it would look to your naked eye. So this is different than the James Webb Space Telescope, because it will be looking at a longer wavelength. So it will slightly dip into the visible spectrum. I think it's 600 nanometers is where it starts, but then it goes all the way up to 28.3 micrometers, which is mid-infrared, and that's nowhere near visible. So anything you would see, you would typically that you could see with the naked eye, that James Webb Space Telescope sees, would be red. That being said, they'll still be able to publish cool images because they'll use false color. So like if there's something at 10 micrometers wavelength, they may color that red, and it'll look pretty in the pictures. So it's not really that much different, because every image you see that's been taken in space has been altered significantly in different ways to to make it look good anyway. So it's really sort of a moot point, not much of a difference there. But it is a big difference because those higher wavelengths will allow it to see further. Specifically, I'm not sure the technical reason on why the longer wavelengths travel further, but I know it allows us to see further into the universe and correspondingly further into the past, because as light travels, the universe is also expanding, so everything redshifts, but also things are so far away that they what the hell was I talking about? Things are so far away that things are like billions of light years away, right? And the universe is only 6-7 billion years old, so I think it's 6.8 maybe. I looked this up recently, and it's super complicated because the universe is expanding, and the rate at which it's expanding is increasing. Obviously, as it expands, right, like the things that are far away are traveling away from us, but they're also accelerating because the universe is expanding, and the further they get, the faster they accelerate. So it's complicated, basically, but there's actually there's a maximum distance back in time that we can see, and then there's also a maximum distance that we'll ever be able to see based on the size of the universe. And there's actually things that we can see now that we won't be able to see in the future because of the expansion of the universe. But this is all kind of esoteric and not related to the James Webb Space Telescope. So basically what's cool about it is it can see objects that are so far away and so redshifted that Hubble could not see them. So that's cool. So everyone's very excited about that because it allows us to get more of an insight into the origins of our universe. Other things about it, the instruments need to be kept very cold because they are infrared. So that's part of the reason it's being deployed at the L2 Lagrange point, which is on the opposite side of the sun, or sorry, the opposite side of Earth as the sun. And that's actually a stable point where its centrifugal force basically perfectly balances the mass of the sun and the Earth. So it'll actually stay there roughly without too much energy being expended by the thrusters on the James Webb Space Telescope. It's also a great place, so that makes it a great place to station because you need less fuel for station keeping, so it can stay there longer with less fuel. It's also a great spot because being on the opposite side of Earth as the sun allows it to have lower thermal noise, which is important for your infrared imaging systems. And so yeah, the primary contractor for this is Northrop Grumman. There have been a ton of issues with it. Its development has not proceeded smoothly. It was originally scheduled for launch in 2007. It is now 2021. It might launch in 2022. Let's not kid ourselves. It's currently scheduled for December 22nd launch. That was delayed from, I believe, December 17th, something like that, because of an incident that happened. Basically, when they were moving the telescope, it had so when it was on the ship, I guess they had a bunch of instrumentation on the telescope that would detect any forces or any impacts, and then measure those and the accelerations caused by that, and from there they could determine the damage or impact, if any, to the satellite. However, in this case, they had removed that instrumentation in order to transport the satellite, it sounds like, and they had an impact, and they're unsure of the strength of the impact. They know obviously what caused it, so they can reproduce it, but they were concerned because obviously this thing needs to work. It's very critical. So if you're familiar with like Hubble, they did a ton of, or I should say several missions to fix Hubble, right? And that's because Hubble is in low Earth orbit. I don't know what the altitude of Hubble was offhand, but a low enough orbit that, let's see, I can find it right here. Yeah, so it's in like a 540 kilometer orbit, so low enough that it was not too difficult for the space shuttle to go service it, because the International Space Station's in a 400 kilometer orbit, so the space shuttle had enough delta V to go service Hubble. However, James Webb Space Telescope is going to the L2 point, which is a long way away and pretty difficult to get to. It is, it is technically, out as escaped from Earth at that point, so not easy to get there, and certainly not easy to get back. For crew, carrying equipment, pretty much impossible with current technology, so there's no fixing it once it goes, which is the problem because it has a very complicated sequence for deployment. I think there's like there are hundreds of single point failures in the deployment of this thing, so that's probably a lot of the reason it's taken God only knows how long to develop, 20, 30 years. I don't know when this started. Development began in 96, so 25 years to develop this thing, and $10 billion. The other reason, of course, is because government acquisitions is broken, but that's a different topic. So, anyway, hopefully everything goes well. It's very cool. It is, as much crap as I give it, it is revolutionary. It's way bigger than Hubble. It's at a better wavelength. It's at a way better spot than Hubble. Hubble did get all the thermal noise I'm talking about right from the sun, and and had other issues. There's even some atmosphere up at 500 kilometers. Relatively minor compared to obviously down here, but other things interfering with Hubble being so close to Earth. The L2 point, not much is out there, and it's cold, which is good for the infrared and for the thermal noise. So this thing has some serious potential. Obviously, astronomers are stoked about it. Time on this thing is going to be very difficult to come by, and I think it'll be cool. So it's slated to launch on December 22nd on an Ariane 5 launch vehicle. The Ariane 5 is an ESA vehicle. I can pull it up, an image if you're interested, but there it is. Cool. So that's the Ariane 5. It has about a 20-ton payload capacity to low Earth orbit, which is higher than like a Falcon 9. Falcon 9 is about 16 tons to low Earth orbit. Well, that's in a reusable configuration. Obviously, the Ariane 5 is expendable, right? And it is ESA's current vehicle. It's slated to be replaced by the Ariane 6, which comes online 22, 23, which looks quite similar and has quite similar capability. Anyway, Ariane 5, I looked into it, so it's actually had like 111 launches, so it's had a ton. It was first tested in 1996. It has obviously had iterations on the launch vehicle since 1996, and with increasing capability with each one, but still, very, very proven launch vehicle, right? So I think there were a couple minor changes, not like a whole new class of Ariane 5, but just a block of Ariane 5, you could say. But there's just a couple very minor changes a few flights ago that NASA was interested in, and all the flights since then have gone well, so NASA is comfortable launching on the Ariane 5 at this point. And yeah, hopefully it launches here in about 20 days. Be very exciting. As Scott Manley said, the James Webb Space Telescope launching on time is just a tale we tell to small children. So, yeah, so we'll see what happens with that. Very exciting. And yeah, I covered the incident. I think that's all I had on James Webb. Alright, so thanks again for watching that, and if you liked it, please like the video and subscribe to my channel. I've got several more news segments coming out that I'm really excited about. A ton of big stuff went on recently, and I've got a lot of pieces on that, so make sure to subscribe for updates on that. And then I'm also going to release some more educational pieces here in the next several months, so be on the lookout for that as well. Alright, well thanks. This has been Comprehensive Rocket Science News Update. See you later.